So this is implicit differentiation, and we're focusing today on the second derivative. Because we've done the first derivative several times. That's the dy dx. We're able to find that. Now we want to be able to find the second derivative. So how do we find the first derivative? Yeah, so the derivative of y squared is 2y dy dx. Okay. And then what do I do? Divide by 2y. So dy dx is 2x plus 2 divided by 2y. Can I simplify that at all? Yeah, so you can, x plus 1 divided by y. So you can factor out a 2 on the top. It's actually, that's why it works. You're right, you can divide by 2 in the entire problem, but that's why it works. So you've got x plus 1 divided by y is your first derivative, right? So the second derivative, how do we find the second derivative? Yeah, you find the derivative of your first derivative, right? That's how you find the second derivative, is you do the derivative of the first one. And this is a quotient rule, so how do we do this? So low times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Alright, so I've got y times 1 is y, minus I've got x plus 1 times 1 is just going to be the x plus 1. And then what do I do about this dy dx right here? Plug in what you got for dy dx. So instead of writing it again, I'm just going to write what it actually was. Okay. Anyone have any ideas? Multiply by, it's a complex fraction, so multiply by what? The common denominator, right? And these are over 1. So what's the common denominator? Y. Okay, so we're going to multiply by y on the top and y on the bottom. Okay. So when I do this y multiplied by this y, what do I get? Y squared. And then this part right here, it doesn't really look like it, but this is considered to be one piece, right? That's one part of the problem. So if I have this divide by y and that multiply by y, what's going to happen? They're going to cancel. And then what do I have left over? Yeah, x plus 1 squared. And I'm going to go ahead and write it out twice because we are going to have to FOIL that. Good times. What do we have on the bottom? Y cubed. Getting a complex fraction in these problems and getting rid of that denominator seems to be a common practice. That's something that's going to show up a lot. Okay. All right. So now what can we do? Yeah, we're going to FOIL this, right? So I've got y squared minus, and what do you get when you FOIL that? You don't have to waste as much paper as I am when you do this if you don't want to. You guys might notice I'm wasting a lot of paper right now. All right, now this is the part that you might be forgetting. Does anyone else remember the other part? Because we did one example like this in the other video. Say it again. Kind of. So one of the things we can do is you can go back to the original problem, and do you see how they told us what y squared equals? And then do you see how right down here we have a y squared? We can make another substitution. So it's kind of like in the middle of the problem, we saw a dy dx, and so we substituted what we knew dy dx equaled into the problem. This one is a little bit more subtle because it's not like, hey, dy dx, that's weird, I should plug something into it. It's like, oh, y squared, I could see that in the original problem. This is another common thing that happens when you're finding the second derivative, that somewhere in the problem you're going to simplify towards the end, and you're going to be able to take something from the original problem and plug it back in. So that y squared right here, is we're going to replace it with x squared plus 2x. Because in the beginning of the problem, that's what y squared was set equal to. And then I can go ahead and distribute that negative. So I've got minus x squared minus 2x minus 1. Yeah, and a lot of stuff cancels out, right? The x squareds do, and the 2x's do, and so we just get negative 1 over y to the third, which is the second derivative. I did not.
Do you mind if we just put F?
You can't say f of x because that's you saying f double prime of nothing. No, because this is the notation that's used, and you'll mess up yourself if you don't know it. All right, we're going to do another example, and then your assignment today only has 4 of these. All right, so not too many. Not too many. All right, second example. Y squared plus 2y equals 2x plus 1. So what do we do first? So I heard 2y dy dx plus 2 dy dx equals 2. I divide by dy dx?
No, it's GCF.
You take it out like a GCF. And so what goes inside my parentheses? And then what do I do? So dy dx equals 2 on the top and 2y plus 2 on the bottom. So I'm going to take this, I'm going to say the top is 2, and I can factor 2 out of the bottom. And so what happens with the 2's? They all cancel. So it's 1 over y plus 1. So what are we going to do now? Yeah, take the derivative again. It's a quotient rule. So the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared and then what do you see? Yeah, so the first part is nothing. We just got to plug in dy dx. So that's 0 minus 1 times dy dx. There's a lot of y plus 1s in there, right? I think you have it, actually. And then flip it up. So we're going to take the top and we're going to leave it the same. And then Emma said we should take the bottom and flip it up. So what does that give you? What's on the top? -1, and then what's on the bottom? Y plus 1 to the third. So the difference between this problem and the example we just did is that in this problem there wasn't a point where we could go back and see it kind of looking like the original problem. There wasn't a substitution where you could take the original problem in any form and plug it back in. But we definitely did see some simplifying we could do at the end there. All those y plus 1s.